Okay, let us continue the part 2 of today's class. Okay, we continue to teach the slides of chapter 3. Okay, please turn to page 130. Since in this example, okay, NT is equal to 4 and R is equal to NR is equal to 3. This implies that we should find that equal power allocation performs 10 times log 10 of 4 divided by 3. Okay, why? Okay, because according to equation 3.41, degradation is equal to 10 times log 10 of NT over R. Okay, so NT is equal to 4 and R is equal to 3. So here we place 4 over 3 and it is equal 1.25 dB. Okay, it is very important to check, okay, if this equation is correct, okay, because the slides or the textbook or papers which you read are not always correct, so you need to check them by yourself. Okay, let us use the calculator, okay, in the Windows operating system. Okay, so let us calculate 4 divided by 3 and take log 10, okay, and times 10. Oh, sorry, not 4 divided by log 3. Okay, let us calculate it again. 4 divided by 3. Okay, no, not this. 4 divided by 3, okay, and is equal to this. And take log 10 and times 10, okay, times 10. Okay, we can see that, okay, it is correct. This value is approximately 1.25 dB. Okay. Okay, worse than eigenbeamforming when rho is large. Okay, let us go back to a figure. Excuse me. Okay, we can see that when rho is large, that is signal to noise ratio is large. Okay, for example, we take this line. Okay, this line as an example. When the bits per channel use is equal to 16. Okay, the equal power allocation and the eigenbeamforming. Okay, the difference between them. Okay, this difference is approximately 1/4 of this length. Okay, and this length is equal to 20 minus 15 dB, which is equal to 5 dB, and 5 divided by 4 is equal to 1.25 dB. Okay, so this proves that the value 1.25 dB is correct. Okay, examination of figure 3.5. Okay, excuse me. Let us go to figure 3.5. Okay, this figure, we have seen this before. Okay, let us go back to page 131. Okay, shows that the equal gain allocation curve is in fact shifted to the right by 1.25 dB relative to the eigenbeam-forming curve at large rho. Okay, let us see figure 3.5 again. Okay, we can see that when the signal-to-noise ratio is between 15 dB and 20 dB. Okay, the curve of the equal power allocation, okay, and eigenbeam forming. Okay, equal power allocation is a shift. Okay, if we shift eigenbeam forming to the right by approximately 1.25 dB, we will find an equal power allocation curve here. Okay. Okay, consistent with this prediction, that is the prediction in the previous page. Okay, at small SNR, 4 eigenbeam forming becomes equivalent to single mode eigenbeam forming, resulting in the two curves merging in that region. Okay, let us go back to the figure again. Okay, we can see that when the signal-to-noise ratio is small, okay, the eigenbeam forming curve, okay, this curve, and the single mode beamforming curve, okay, this curve, they merge into one curve, okay, this one. Okay. Okay, so this phenomenon is the same regardless of whether NT is greater or less than NR. Okay, let us see the previous subsection. Okay, the previous figure. Okay, in figure 3.4, we can see that the eigenbeam forming curve, okay, this curve, and the single mode curve, okay, merge together, okay, when signal to noise ratio is small. Okay, good. Okay, next let us go to section 3.8, capacities of SIMO and MISO channels. Okay, the theoretical expressions for the capacities of SIMO and MISO channels have particularly simple forms that help lend useful insight when comparing these two multi-antenna configurations. Okay, because we already have the theoretical capacity of MIMO channels. Okay, so SIMO channels and MISO channels are special cases of the MIMO channels. Okay, so we can easily get the theoretical expressions for the capacities of SIMO and MISO channels. We derive and discuss these expressions in this section. Okay, next let us see section 3.8.1, SIMO capacity. Okay, first let us see the CSIR only case. Okay, CSIR means channel state information at the receiver. Okay, so now only the receiver knows the channel state information. That is, know the channel matrix H. Okay, we start by considering a SIMO system under the CSIR only assumption. Recalling that in general, the square of the forbinions norm of H is equal to summation I is equal to 1 to R, where R is the channel rank, lambda I. Okay, where lambda I is the i's largest eigenvalue of the channel, of the matrix H times H Hermitian. Okay, then under the Simon assumption, the square of the Frobenius norm of H is equal to lambda. Okay, again, the equation number is in the wrong place. Let me fix this problem again. Okay, good. Okay, where lambda is the eigenvalue of H times H Hermitian. Okay, so please note that here is the word the. Okay, it means that lambda is the only eigenvalue of H times H Hermitian, or the matrix H times H Hermitian only has one eigenvalue. Okay, do you know why? Okay, let us see the handout. Okay, page down. Okay, page down. Okay, so let me see. Okay, here. Okay, page 136, problem 1. On this page, the author wrote, where lambda is the eigenvalue of H times H Hermitian, does it mean that H times H Hermitian have only one eigenvalue? If your answer is yes, prove it. If your answer is no, then give a counter example. Write down the correct statement and prove it. Okay. Solution, it is left to you as an exercise. Okay. I believe that you should be able to solve this problem. Okay. After you taking the course linear algebra, and I know that you have taken the course linear algebra when you are a freshman. Okay, let us go back to the slides. Okay, so okay, change the pointer. This expression follows from the fact that R is equal to 1 for a full-rank Simon channel. Okay, why R is equal to 1 for a full-rank Simon channel? Okay, let us see handout again. Okay, page 137, problem 1. Show that for a full-rank Simon channel, the rank of the channel matrix H is 1. Okay, solution. It is left to you as an exercise. Okay, because you have taken the course linear algebra, so I think you should be able to solve this problem, okay, by yourself. Okay, let us go back to the slides. Plug in equation 3.42. Okay, this equation 3.42. The square of the Frobenius norm of H is equal to lambda into equation 3.11. Okay, let us go to equation 3.11. Okay, in equation 3.11, the capacity is equal to, again, the equation number is in the wrong place. Okay, good. Okay, so in equation 3.11, the capacity is equal to summation I is equal to 1 to R log 2 of 1 plus rho over NT, okay, times lambda I. Okay, Now we are consider the SIMO channel. So NT is equal to 1. It means that the number of transmit antenna is equal to 1. And R is equal to 1, okay, which is an exercise for you. So there is only one term in this summation. And the lambda, okay, we do not need I because we only have one lambda, okay, one eigenvalue. And the lambda is equal to the square of the Frobenius norm of H. So finally, okay, so yields the following expression for the capacity. C SIMO CSIR is equal to log 2 of 1 plus rho times the square of the Frobenius norm of H. Okay, again, the equation number is in the wrong place. Let me fix this problem. Okay. Okay, good. Okay, next page. Excuse me. Okay, since the square of the Frobenius norm of H is equal to NT times NR, it follows that for a SIMO system, the square of the Frobenius norm of H is equal to NR. Okay, because for a SIMO system, there is only one transmit antenna. Okay, so NT is equal to 1. So we can cancel the term NT, and the remaining term is NR. Okay, so we can rewrite equation 3.43. Okay, let us go to equation 3.43. Okay, it is this equation. Okay, C SIMO CSIR is equal to log 2 of 1 plus rho times the square of the Frobenius norm of H. Okay, so C SIMO CSIR is equal to log 2 of 1 plus rho times NR. Okay, again, the equation number is in the wrong place. Let me fix this problem. Okay, it is 3.44. Okay, good. Okay, this expression shows that for a SIMO system with CSIR only, the capacity increases as the logarithm of NR when rho becomes large. Okay, why? Because when rho becomes large, okay, rho NR also becomes large. Okay, and we can assume that rho NR is much larger than 1. Okay, so we can omit the term 1. Okay, so it becomes log 2 of rho times NR. So the capacity C increases as the logarithm of NR when rho becomes large. Okay. Okay, how does this expression compare with the capacity for a full rank N by N system given in equation 3.17? Okay, let us see equation 3.17. Okay, in equation 3.17, C is equal to N times log 2, 1 plus rho. Okay, oh, again, the equation number is in the wrong place. Let me fix this problem. Okay, good. Okay. So in order to conveniently compare this case, okay, n by n full rank channel with equal eigenvalues. Okay, let me copy this to write it on the blackboard. Okay. Of course, I do not have a blackboard now, so let me use the Microsoft Word instead. Okay. Okay, like this. And okay, let us back to page. Okay, let me see, maybe 140. Oh, not this. Okay, so let us go to page 138. Okay, then this is the CSIR. Okay, and copy here. Okay, and this is equation. Oh, I cannot input the. Oh, okay, 3.44. Okay, so this the SIMO channel with CSIR only. Okay, let's make this bold. Okay, so now we can compare these two equations. Okay, let us go back to the slides. Okay, as we saw earlier, the capacity of a full-rank n by n system, system with equal eigenvalues increases linearly with the number of antennas. Okay, let us go to the blackboard. Okay, we can see that for the n by n full-rank channel with, okay, let me enlarge the font. Okay, with equal eigenvalues, the capacity C increases linearly with the number of antennas. Okay, n, where n is the number of transmit antennas and the number of receive antennas. Okay. So let us go back to the slides and compared with logarithmically in the SIMO case. Okay, let us see the SIMO case. Okay, in the SIMO channel with CSIR only, we can see that the capacity increases with the log NR, where NR is the number of receive antennas. Okay, so this one is the linear relation, and this one is the log relation. Okay. Okay, next. Okay, change the pointer. Although it is clear that the capacity of an n by n system should be larger than a SIMO system. Okay, of course. These expressions provide a quantitative comparison. Okay. Next, let us see CSIR plus CSIT case. Okay, since SIMO systems only have one transmit antenna, there is nothing the transmitter can do to exploit its knowledge of the channel. Okay. Therefore, it is 25 minutes. Let us take a break.